Okay, this event does not start with a hook, and I hope you'll stay with me anyway. This is an investigation of the idea of proportionality, um, and then the subtitle, A Tool for Discovering Relationships. And that is something that I believe very passionately about. We will, as we go through the year, we will come up with new ideas, and we'll realize that they have a relationship to some old ideas, and then we will try to figure out what their relationship is. And we will discover that relationship through the vehicle of proportionality. So you do have there in your notes rather extensive development of this that you can follow along and try not to get too bored. You also want to fill in the worksheet as the opportunity arises. And I'm sorry, I may not do a very good job of prompting you when it is time to do a worksheet, so keep your eyes open. But here is some data about how many cigarettes people are smoking every day and what percentage of that population develops cancer after 20 years. And the question is there a relationship between your cigarette smoking and your lung cancer? Clearly, people who are smoking more cigarettes seem to have a higher incidence of cancer. Well, that's called a direct relationship, I believe, but it's not the same thing as a proportionality. For it to be a proportionality, it would need to be that when you double one, you double the other. More exactly, if one is multiplied by a factor, the other variable must change by the same factor. So triple one, triple the other, or quadruple one, quadruple the other would also work with proportionality. I find this just a very handy little tool to remind myself. Well, you look at that data, and here's a doubling. If this were to double, that would be 24. Ooh, is it close enough? Here's a tripling. If this were to triple, it would be 36. Whoa, not so good. Here's a doubling. If this were to double, it would be 54. Whoa, it doesn't look exactly like double one, double the other, but maybe it's close. Well, it's very hard to judge with numbers, although I will ask that of you. But if you take that data and graph it, cancer as a function of cigarette smoking, if you look at that data, that looks like a very strong relationship there. Again, a linear relationship, if you can put a straight line through it, but if that, oh, come on now. There we go. But if that straight line you put through the data also passes through the origin, then, and only then, would we say it is a proportionality. Is it the case that double one, double the other? And that ought to be very clear in just a few minutes. Oops, we don't have room. Sorry to not be so efficient here. Oh, come on, be a line, will you? There we go. Okay, we'll just leave this alone here. That if we decide that cancer is proportional to the rate of aging, we would write that cancers are proportional to, I'm sorry, not aging, but smoking cigarettes. It's me who is aging. This symbol here, this is the Greek letter alpha, but it's really supposed to be more of a fish, is read is proportional to. Or we could use the letters C and S. And if they are proportional, if you can write it as a proportionality, then to get from a proportionality to an equation, you just replace the proportionality symbol by an equals, but you also have to throw in this constant of proportionality. But look at this. This is indeed the equation of a straight line with a y-intercept of 0, that is passing through the origin, and a slope of k. So I think you can see that if doubling this means that s doubles, then it should be graphed as a straight line passing through the origin. Let's do some practice, not with graphing, but just looking at these numbers. Look at these 5 sets of data and pick out the ones which are direct proportionalities, where doubling one means you double the other. And we'll look at that when we get back to class and see if we can agree. Here is a set of data about how much food you get and how many people are in the party. And it seemed like when one person was around that person was getting 6 slices of pizza on the average. When 2 people are around, they're each getting 4 slices. When 4 people are around, they each get 2 slices of pizza. When 7 people are around, you get 1 1/4. Clearly, there's something happening here. As these get bigger, these get smaller, what we call an indirect relationship. But if it is the case that when you double one, you have the other, ooh, close, oh, perfect, double, have, this would be times 7 halves, is 4 times 2 sevenths, that would be 8 sevenths. Yeah, it's somewhat close to this. If double one, have the other is the relationship that you have, then we call that an inverse proportionality. Technically, it would be if one changes by a factor of x, then the other changes by the factor of the inverse of x. So if one changes by a factor of 2, the other changes by a factor of the inverse of 2. If you take such data, not a direct proportionality, but in this case we're hoping it's an inverse proportionality, and graph it, clearly it is not a straight line passing through the origin. It is instead a swoop that kind of nests on the axes. If that's what you see, then you suspect it is an inverse proportionality. This was pieces to people, but if it's an inverse proportionality, what you would say is that people is proportional to inverse. People, we would read this, pieces are inversely proportional to people. But look at that. That's the same thing as pieces are directly proportional to inverse people. And that's exactly what we're going to work with. That we will take all of the people and I will turn them into inverse people by making them be the denominators with the 1 in the numerator. So 1 over 2, 1 over 4, 1 over 7. But I strongly encourage you, don't write 1 over 7 and 1 over 4. Decimalize them, or you will get into trouble. And now, instead of graphing shares of pizza versus people, I'm going to graph shares of people versus pizza versus inverse people. This quantity, this as a function of these values here. And if you do that, the data gets transformed. Instead of the swoop we had when it was people here, when it's inverse people here, it turns into something which much more resembles a straight line. And if I really pushed my luck, I could even force that straight line to go through the origin. Now, this is open to discussion. You could say, no, you force that. That's not really straight. It's in fact an arc. And it doesn't really go through the origin. It ought to be a little bit more up here. Well, we can have an argument. That happens. Data does not speak for itself. It has to be interpreted. But it would not be ridiculous for me to state that the relationship is an inverse proportionality, and the evidence would be that I claim I see a straight line passing through the origin. So pieces are directly proportional to inverse people, which is the same as saying pieces are inversely proportional to people. But when you are doing a lab and the data comes out as a swoop like this, you will then need to make a second graph in which you take the values on the horizontal axis and take the reciprocals of them, and you will be able to look at that data and judge whether it is an inverse proportionality. This curve is in fact a hyperbola, but I do not trust you to make that judgment. Oh, that's a hyperbola, not a parabola. It's not a section of an ellipse. No, you can't do that with your eyes. But with your eyes you can make a judgment about whether it's a straight line passing through the origin. New topic. Combining proportions. First off, if A is proportional to B, then it is true that B is proportional to A. That is a reciprocal property. That's also true for equality, that if A is equal to B, then B is equal to A. That's the reciprocal property. Reflexive property. And also it works with inverse proportions. If A is inversely proportional to B, then B is inversely proportional to A. But then comes the matter of putting proportionalities together. And if it were an equation, and we said that A is equal to B, and B is equal to C, then we would know that A was equal to C, and that's called the transitive property of equality. Well, there is no such transitive property for proportionality. Instead, if we want to find the relationship of A to C, we need to have a common variable. We use this kind of reflexive property to get the common variable on the left. And then that same common variable is proportional to the product of the two values on the right. I hope that works for you. We will apply it. First, I'm going to go through an example to justify this. You might say, Mr. Houghton, prove this to me. Well, I can't. I have tried. It just does not yield itself to a nice mathematical proof. But it is true. Trust me. Here is the development of the universal gas law, which is a relationship between pressure, volume, and temperature. Oh my. My tool for discovering relationship is proportionality, but that only finds relationship between a pair. So what I need to do is to hold one of these three constant. I will hold pressure constant, and I will look for a relationship between the other two, volume and temperature. And what I do is I set up an environment where this lid, if the pressure inside goes up, the lid will get pushed up. So this is always atmospheric pressure in and outside of this container. And then what I do is I feed some energy in, causing the temperature of this gas to go up, and I watch this thermometer. Oh, look how much hotter it got, and the volume got greater. And what we discover, I think this is called Boyle's law, maybe, is that the volume is proportional to the temperature. that has to be absolute temperature, but when you double the absolute temperature, you do double the volume, if the pressure stays constant. One relationship established. Then what I'll do is hold the volume constant. I put it in a rigid container. The volume will stay constant, and I'll look at temperature and pressure. So again, I feed energy in, the gas gets hot, which I'll record with the temperature, and I look at the pressure in the container, and boom, lo and behold, again, when you double the absolute temperature, you double the pressure, which might be called Gay-Lussac's law, but I'm not sure. I don't think it's called Charles's law, but it might be that too. So, what we then have are the relationship between volume and temperature and pressure and temperature, but that T is on the wrong side. So I use the reflexive property to rewrite it so that the common variable is on the left for both of these, and then that common variable is proportional to the product of the two on the right. As an equation, I introduce a constant of proportionality. I then move that constant of proportionality over to the other side, and I replace the constant of proportionality by the number of moles and the universal gas constant, I think it's called. But you ought to recognize that. There is the universal gas law. And it is a relationship between temperature, pressure, and volume. And I firmly believe that in the history of science, this law was found by combining proportionalities, just as we have just done. Okay, and now some practice. I give you a table of numbers. I would like you to start by looking at that table of numbers, just examine it to see which one of these three. You can circle the one that you think it is. Is it an proportionality, an inverse proportionality, or neither? Then after you have made that choice, please take the time to graph the data and look at it to see if that graph is the kind of graph you should have gotten for the choice you made here. And if what you get is a swoop, which would correspond to inverse proportionality, in this instance you do not need to regraph it. That would be asking too much of you. But in a lab, I would expect that of you. Again, new pair of data points, and you choose which one it is. And then after you have gone through that and made that choice, then graph it and see if it graphs the way it should for the choice that you made there. Just don't do any graphing here, but just look at these and decide what the relationship is between these pairs of variables. Then what I want you to do is yet another problem where, given these two relationships, will you please combine them into a relationship between all three variables, and then the same thing here. And that is the end of your tasks for today. Thank you.